So in this section of the notes, what we're going to be talking about is applying our knowledge of redox reactions and how that applies to the natural world. So the first thing that we're going to be looking at is what is a battery. So a lot of you have cell phones, laptops, iPads, and all of those things have batteries. So what exactly is a battery? Well, we know it's some type of device that produces electricity or power in order for something to operate. So let's take a deeper look. As we look at what is a battery, we have to think about a voltaic cell. Most batteries that we deal with are voltaic cells. So I want you to consider the following single replacement reaction, looking at zinc and my copper sulfate. So looking at these two things, why does this reaction occur? So looking at table J, this is something we looked at when we talked about single replacement, and we're looking at the activity of zinc in comparison to that of the copper. So we know that zinc is actually more reactive than that of copper, and since it's more reactive, we know that this is actually going to be a spontaneous reaction that'll take place all on its own in nature. So assigning oxidation states to the elements in the reaction. So when you're looking at the following here, who's being oxidized, who's being reduced? Well, Leo is a positive dude, and who becomes more positive? Well, we can see the zinc becomes more positive. We know the charge on a zinc is a 2+, so we know that zinc is going from a 0th charge to that of zinc with a 2+. So who's being reduced? Well, reducing we know is negative because a gain electrons reduction. Who gained those 2 electrons? Well, we know copper did. So copper actually went from a 2+ ion to that of a neutral atom in this case. And it just went to being Cu. Okay, so when we're looking at this, I want you to write the half reactions of the oxidation. So we know that we went from zinc with a neutral charge, and we produced zinc. Oops, I apologize for the writing. Zinc with a 2+, and we added 2 electrons there. So who is reduced? Well, in order to have oxidation, reduction also has to take place. So we know that our copper with our 2+ charge picked up those 2 electrons, and as it added those 2 electrons, we know it now became nice neutral copper. So something that takes place all in the natural world, all by itself. So when we look at voltaic cells, there's a summary that we have to take into account. There's 4 big key parts. So the species being oxidized always has to be higher on table J, and we call that the anode. Okay, and we can talk about it as the anode because it's the A negative ode. So why is it the A negative ode? Because we lose our electrons, we give those off, so that's the negative side. Opposite of that, we have the species being reduced, which we call the cathode. Why is it called the cathode? Well, because now it's becoming less positive because it is taking in those electrons. So remember, Leo is positive, so anode. Reduction, is negative, so that's the cathode. Third point here is the species being oxidized gives the electrons to the species being reduced. So the oxidized, or the anode, always gives to the cathode, A to C, alphabetical order. So we can now harness this transfer of electrons from an oxidation redox, and that's actually what a voltaic cell is, and we use this to produce electrical energy. So going back and looking at table J, you can see that in this case zinc is higher up. So since zinc is higher up, we know that is the anode, and we know that copper acts as the cathode. Remember, voltaic cells is a device or an electrochemical cell that spontaneously takes chemical energy and changes it into an electrical energy. This is done by separating the oxidation and reduction half reactions, causing electrons to flow in a specific direction, causing an electrical current. So again, flowing from the anode to that of the cathode. And this is how we harness power inside of batteries. So to look inside of an actual battery, you can see that we have zinc and we have our copper. And using that same exact example that we used before, you can see that the zinc electron passes to that of the copper, so acting as the anode, the negative side, passing that to the copper, which is the positive side. One major thing to complete the circuit that you must have is a salt bridge, which allows for free-floating ions to pass from that of the anode side to that of the cathode side. Again, this is all electrically driven because of that desire to obtain or lose electrons.